So yeah, I have pretty loaded background, and if you're interested, kind of it's all started by just kind of working on my PhD in physics by simulating physical processes. So by doing that, got exposed to high performance computing because like I need to optimize the code we were writing as close to the hardware as possible, right? And then kind of while trying to analyze all those protein complexes, decide, oh man, like it's really difficult to just look at that and label it, can manually label them. So decided to use a little bit of machine learning. And you can imagine it was more than 10, 12 years ago. Oh my God, I'm old. So anyway, I got exposed to basics of machine learning and kind of went from there. Was working as a consultant engineer for several years until I built enough expertise to write a whole book about parallel programming and code optimization. And then kind of, transitioned into that evangelist / developer advocate role when I was helping developers to learn more about how they can code more efficiently, right, or use the hardware more efficiently. And it seems like now I'm doing similar thing with quantum computing. So basically helping others to understand where they can find the most useful information about quantum computing, how they can use the hardware the most efficient way. And for those of you folks who don't know what IonQ is the company we're using trapped ions technology as our quantum computer implementation. So basically it's ytterbium ions, which kind of float on top of the chamber, and Harmony, Aria, Forte. Actually, that was one of the questions I previously had. What are those? That's our different types of different generations of our quantum computers. Forte is being the latest one. So my plan for today is to basically talk a little bit more about the hardware, because I find this topic very fascinating, and a lot of people, when they kind of understand what is physically happening on the hardware level, it's easier for them to also understand the optimization techniques, right? Or basically how to use it the most efficient way. So I will talk a little bit about the physics of quantum computers, what's happening basically in your trapped ions, right, chambers. We'll talk about native gates, what type of operations, how we actually engage with those ions floating in the high vacuum, very chilled, not kind of microkelvin chilled. Our temperature is around say 5 to 10 kelvins, but like it's still pretty cold enough to prevent all other molecules, right, or atoms flying around and decohere the state of the ion. So that's why the fidelity of trap ions are pretty high. It's naturally quantum. So we'll talk about native gates. I will talk a little bit about debicing and sharpening after that. That's the techniques for error mitigation used in IonQ. And my whole talk, I'm planning to probably finish around yeah, it will take about 45 minutes, and I will have 5 to 10 minutes to answer the questions after that. So that's the plan. Before we actually jump into the talk itself, let me show you how easy it is to use quantum computers, specifically IonQ quantum computers. So right here, I have AWS, brackets, opens, right? Oops. I apologize for that. So you basically have devices already available, right? There are several of them. And some of them are actually in the maintenance mode right now, right? Some of them you actually going to need reservation, which can be done through Bracket Direct. So if you go here, and IonQ Forte will allow you to basically reserve the device for your research purposes. So if you take a look, there is this somewhat mystical phrase with error mitigation, right? And I mentioned previously that we have debicing and sharpening. That's what error mitigation is for IonQ devices. All right, so it's pretty easy to use them, right? And there are several examples even coming from the default notebooks. I believe if you just look at the documentation, it's available on Amazon Braket. We publish kind of similar materials with Microsoft. So Azure Quantum have the examples where you can simply look at the practical usage of error mitigation, how to submit the job to our simulators or to our QPUs. By the way, access to the simulators are free. So also, let me actually go to the IonQ.com. That's kind of our main website where you can find a lot of useful information about our plans, about our technology. That's actually how the chamber itself looks like. It's actually pretty small. It's about kind of that big, and it simply kind of keeps the ions floating on top of the chip with changing electromagnetic fields and also constant field by which helps to kind of squeeze those ions together in one chain. And that's actually going to be pretty important when we entangle into qubits, but I'm going to get to that in a second. So we supporting all three major cloud providers at this point, so AWS, Microsoft Azure, as well as Google Cloud. Majority of the languages supported as well, including PennyLane. So I will be talking about this in a few slides as well. If you want to learn a little bit more kind of with the practical examples, I would recommend to go to resources, go to Resource Center, and there will be a lot of documentation covering kind of how you can start, let's say, with Cirq, with Qiskit, PennyLane as well. So that's basically probably going to be the most useful resource to go and find information and read more about how you can code for IonQ quantum computers. So now let's go back to my slides and talk about physics of quantum computers, because I find it very fascinating. So the whole device, the chamber itself, is pretty small, right? It's about kind of that big. But you need to provide a lot of optical system, stabilize the electrical circuits, because the way how we control where the lasers are directed, right? All of that is done with the acousto-optical deflectors, and like you need to be very, very precise what the potential difference you put on top of those. Well, basically, it's a kind of piezo element, but all of that requires quite a bit of real estate. But overall, what you got out of that is the chain of ions, which sitting basically on top of that inside the chamber with a high vacuum, chilled down to, as I mentioned, temperature around like 5 to 10 kelvins, so that those ions can preserve their quantum state for almost like hours. Honestly, it's the fidelity of their state is pretty high, right? So that's the kind of beauty of the trapped ion technology. But well, I need probably to say what is bad about this technology as well. And if you kind of familiar with different implementations of qubits, the gates are pretty slow compared to superconducting implementations, right, or optical ones. Yeah, that's kind of the downside of having trapped ions. But there are also a lot of benefits, right? It's naturally quantum, it have very long coherence time, and so on and so forth. So that is kind of diagram which is supposed to represent the all-to-all connectivity available in the IonQ QPUs. And basically what it means that with one MS gate, with one gate operation, we can entangle pretty much any ions in the chain we have. That is kind of different and beneficial compared to, let's say, superconductive systems, where you need to have kind of physically co-allocated or kind of closely allocated qubits, right, to basically make them entangle, to share the quantum state. In our case, in this chain, we can address pretty much like any ion and make them entangle So there is no need for swap operations to move the your qubits closer to the other one, right? And then probably move it somewhere else. And I find it pretty beneficial for our implementation. Now about the native gates, just to kind of give you more ideas what's actually happening on the physical level of the devices. Usually native gates, it's very advanced topic. Not everyone needs to use it. I mean, you can use the standard gate set with your Hadamard, CNOTs, and you're gonna be fine. Native gates is usually gonna be needed for somebody who's developing compiler or working on error correction, error mitigation techniques, right? Because you need to go down and basically directly work with the hardware to basically get rid of this black boxiness of the compiler, because compiler, the one we have, is doing a lot of optimizations, a lot of even error mitigation techniques, right? It will basically change the way how the circuit is actually implemented on the low level. So you can think about native gates as, if we're comparing it to the classical computer, it's basically almost like using an assembler instead of your, I don't know, C#, right, or Python, which is completely high-level languages, right? So once again, native gates, it's not for everyone, but I still find this topic very interesting because it explains what's physically happening on the device, right? And everything happening when you submit your circuit on the high level, it goes through the compilation stage and optimization steps. So compiler is actually pretty smart. We have really amazing people working on the compiler team who's just doing all sort of heuristical optimizations and tricks to get the maximum out of the hardware based on your, I can probably call it high-level abstraction circuit, right? What compiler is doing also behind the scenes, if you enable error mitigation, it's this debasing and sharpening techniques, it will also create the symmetric variance of your circuit, which will be executed to, I guess the basic idea is to get rid of systematic error. So if you have, let's say, under rotation somewhere, right, but then you kind of flip-flop the circuit, for example, change the order of the qubits you're using, right? So your ions will be in a different order, but the circuit will produce the same result, but you might compensate for that under rotation. That's kind of the main idea behind the devising and sharpening. It's the aggregation techniques which helps you to get rid of the noise a bit. But we will get back to it. So basically, that's what's happening on the compiler side, right? Or you can kind of completely overstep and submit your native gates directly. Right, and then native gates, kind of when the circuit is analyzed, it's kind of this intermediate representation translates into pulse representation. So basically, what actually, how the radio frequency package looks like, which is going to be modulated on top of laser. So that's how we actually interact with the ions. And then you you kind of run your circuit multiple times, right? As many shots you specified in your code, and simply aggregating the result. And based on the type of aggregation you've selected, right? Just your standard average or the sharpening technique, which you're going to be using plurality voting. It will give you slightly different results. But once again, give me just a couple of minutes. I will get to that topic. So that's the compilation process, right? And I specifically was mentioning those native gates. So on the previous, well, 2 slides ago, actually, I was showing this all-to-all connectivity diagram, right, which were just basically represented as a circle. That's not what's happening on the physical level. On physical level, we have this chain of ions, right, which basically hold in one place by changing electromagnetic field. I guess I will try to a little bit simplify and explain how that's actually happening. So imagine that with electromagnetic field, you're creating basically like a saddle potential, meaning that if you have the chain basically along, let's say, this axis, the potential is helping it to kind of push the ions to be in that direction, but they might actually slide down in the orthogonal or perpendicular direction. But if you change the electromagnetic field quick enough, your ions basically almost like sitting in this well, right, and not going anywhere. So that's what we use to keep ions in the same kind of chain in one location, but they still can probably move around one of the axes. So because of that, to kind of keep them all together, we'll also use constant electric field, and with a Coulomb force, we're simply pushing ions at the ends to squeeze the chain together, right? And those ions are pretty close to each other. So even on the image right here, I put the number, so 5 microns. That's the distance between the ions. But we have acousto-optical deflectors, which can take the original laser beam. Basically, there is a splitter which splits it into 2 parts, and this AODs, so acousto-optical deflectors, they can target even individual ions. So for the two qubit operations for the MS gates, when we entangling 2 qubits, that's kind of what's happening physically on the low level in the QPUs, right? We taking one source of the lasers, we're splitting it, and then with acousto-optical deflectors, we kind of modulate the laser beams with radio frequencies. The profile of that package, the duration, as well as kind of initial phase, will control what exactly we're doing with the ions, kind of how we engage with them, right? And actually, we only have 3 physical gates implemented and 1 virtual. And I will get to it in a second. But yes, if we kind of doing 1 qubit operations, it means that we only need 1 laser and kind of point to a specific ion we targeting, right? So our 1 specific qubit, and do some manipulations there. And if you want to entangle 2 qubits, you just basically use the splitter and acousto-optical deflectors to address those ions you want specifically to entangle. So that's what's happening on the low level. I like this slide because it actually shows those operations, right? On the left side, we have single qubit rotations. And as I mentioned, 2 parameters we can control is basically the duration of how long is the package itself, right? Photonic package, or how long we engage with the ion, and that will change the amplitude of the rotation. And second thing, what we can control is basically phase, right? Where the phase is shifted, and that will define the direction of the axis. So it can be X or Y, and then rotation, kind of the longer the duration of the package, the more we're going to rotate it around, let's say, Rx or Ry. And for the RZ rotations, just because we kind of have those ions rotating naturally, we simply, I think I mentioned that we have like 3 physical gate implementations and 1 virtual. So RZ is virtual. The way how it's implemented, the compiler, when it's doing this intermediate representation, transcription, I guess I can use this word, it's simply counting how long do we need to wait between particular gates, and it can calculate how much our rotation around the axis happened. right? So basically, all those RZs, we're not even physically engaging with the trapped ions. We just simply wait a particular amount of time, and we just know by calculating how much the rotation actually happened, right? So that's your rotations. RZ, RYs, and RZs. So it's all controlled by just basically how long you engage or interact with your ions, and what was the phase shift. For the 2 qubits, I find it very interesting. Remember, we kind of addressing the ions we want to engage, and what happened. The way how I visualize it to myself, or can I interpret to myself, we simply allowing those ions we interacting with almost like create a standing wave. I mean, like it's oversimplification on a lot of levels, but it helped me to kind of visualize what's happening there. And that's why we need those ions to be close another. And good interpretation I've heard also is that we pretty much like have a virtual qubit represented by these phononic modes. So when you have those kind of vibrations, and they actually have to be phased, is that even a word? We're kind of in counter phase. In this case, you can introduce additional parameter to the Hamiltonian, right? And kind of pretty much like pumping a little bit more energy with your laser beams into those ions, but like a frequency used specifically not to excite them, in which case they're going to release the photon, right? But it's actually in between the bands to provide kind of to engage with them, and engage with them in such a way that pretty much your ions start sharing the same quantum state. Once again, oversimplifying drastically, I apologize for that, but I'm trying to kind of explain how I visualize it in my mind when I'm talking about quantum quantum systems, but still trying to have more or less kind of classical visualization. So anyway, with 2 qubit gates, that's what's happening. We simply can addressing those ions. We put them into almost like creating, yes, this phononic mode, additional mode. If you prefer, if you want to read more, the first link right here, Molmer and Sorensen, or MS gate, that's what we actually implementing on the low level, and that's kind of the gates we physically have. If you prefer more tensor or matrix representation, that's kind of the operations for all four gates. And yes, I mentioned previously that RZ is virtual. And GPI2, that's your single qubit gates, right? And depending, as I mentioned, phase change, it will simply change the orientation, or kind of define the axis around which we are doing the rotation. And the MS gate is your entanglement gate. So your classical full set of gates can be easily translated through, or expressed through those 4 gates. So that's the example of C0, which actually looks like like 4 single qubit gates and 1 2 qubit gates, entangled gates, MS gate. So if you want to learn more and kind of dig a little bit more in details, I definitely recommend to go to IonQ Docs and look for Getting Started with Native Gates publication. There will be more explanation about those gates and what they actually do, and more of that. So it is available through, well, I'd say majority of the popular quantum languages. So example of using Qiskit, how you can use Qiskit to program or express your circuit in native gates. You will just need Qiskit IonQ. Just import those GPI gate, GPI2 gate, and MS gate, and then you can simply express your circuit explicitly with those gates. Same goes for circ, right? You can just get them from INQ native gates, and ta-da, PennyLane. So if you want to read more, just go to inq.com, docs using native gates with PennyLane. I believe you just need to install the library from the GitHub, and then GPI, GPI2, and MS gates will be available to you, so you can just use them even in PennyLane if you want. Right, so that's what's happening on the low level, right? So that's how we use lasers to interact with ions. Ions, if you remember, is just positively charged particles. We use ytterbium. It's a pretty heavy element. The reason why we chose ytterbium specifically, because it is heavy, so it's easier to keep it in one chain. Plus, ytterbium have 2 electrons on the outside orbital, so it is easier just to take one of the electrons out by, for example, once again engaging with neutral atom first with ions. So we heating up the source of the ytterbium, right, with ions, and then they get trapped into the electromagnetic field and populate the chain. All right, so that's physics. Now let's talk about debicing and sharpening, and a little bit about debicing and sharpening. I showed you the Amazon bracket previously, right, and somewhat mystic message that those QPUs are with error mitigation support. So I wanted to share a little bit more about what the error mitigation is, and that is specifically this debicing and sharpening techniques. A little bit of schematics. I hope I can explain what is debicing and sharpening using these diagrams, but if you want to read more, there is the whole archive paper written by our compiler programmers. They go into this technique, motivation behind it, and the implementation details in more details. So let's start with debicing. So what is debicing? What is that error mitigation technique? And if you are not super familiar with error mitigation versus error correction, we do not detect errors happening with the qubits, right? But we reducing the error accumulated during measurements or during during the execution of the circuit. And let me get into details how that actually implemented. So when you submit your circuit, and for Amazon bracket, I believe you need to specify more than 2,500 shots for debicing to be enabled. And what our compiler will do when the job will be delivered to QPU through AWS, it will, during the completion stage, create 25 or about 25 different variants, symmetric variants of your circuit. What does it mean? It will be doing some manipulations. I mentioned it previously. It can just swap the qubits we're using. So qubits in our case is just the ions, right? Ions in the chain. It can actually move your circuit to neighboring qubits, right? And if there's any systematic error, right, with the state of the qubit, the whole idea of the symmetric variance, flipping, moving, we also modify the profile of this package itself, right? So how the radio frequency modulates the laser beam. So it can be probably just flipped completely. And if there's any under rotation and or over rotation, right, or some of those kind of systematic errors, the whole idea is that those symmetric variants will help you to compensate toward those errors, because they simply going to cancel out. Kind of that's the very basic idea. So we're not checking for the errors, but we're using this technique to minimize them. That's why it's not error correction, it's error mitigation. Right? So that's what the left side of the image, those A's and B's, supposed to represent. So what we're doing, we're just basically looking at those different variants, right, using different qubits, and they then contribute to the answer. Second part is sharpening. Sharpening, it's the way how you look at the results. So if you just simply, so let's say we have results from the symmetric variants, right? And we observe different results. If you just can look at all the results given to you and just aggregate it, you will see those erroneous or errors, right, due to quantum noise, the results which were caused by this quantum noise. And it's pretty common, right? We are living in the in the noisy quantum computers era. So how we can fix it, instead of by aggregating full statistics, looking at absolutely all the results, what we can do, we can just simply, remember we have those like 25 more or less symmetric variants. So we can actually get results from those and only collect the results which are going to be present the most. So the idea behind this statistics aggregation is that we're going to be using plurality voting. Plurality voting, if you're from US, you might be familiar. It's basically the most observed result is going to be counted as the correct result. You have to know one thing, though. This approach, so sharpening technique, is great. It helps you to actually get rid of these noisy contributions, right, and only amplify the correct result. But your problem have to have those kind of single or maybe just a few, but more or less actually probable answers. If your problem, let's say something like quantum chemistry problem, when you're trying to simply build the profile, right, because you're modifying your parameters just a little bit and trying to find extremum, which is minimum or maximum, depending how you define the problem, this technique will ruin your results, right? Because it will be amplifying some of your kind of pick some of the contributions, right? So you will not get this nice energy profile where you're going to be looking for the experiment. So once again, I need to amplify, or kind of I need to say you over and over again. Sharpening technique is only good for the problems where you have a single peak, or maybe just a few multiple peaks. So let's say if you have what type of problem? Hidden shift problem, right? Or somewhere where you're just looking for factorization, right? In factorization, we might have just a couple of contributors, but majority of the rest is going to be just close to zero. And they are close to zero only because of the quantum noise. And if you just dump that noise, right, and amplify the correct results, that's where sharpening works the best. All right, so that's the whole idea behind debiasing and sharpening, right? And it's overall called error mitigation. So in the archive publication, which I referenced previously, and actually will be linked here as well, there is the whole mathematical explanation why it works. And if we just look at principal component analysis, it actually demonstrates that errors are reduced significantly by using those techniques, using just toy samples, using 4-qubit circuits, right? But also bigger ones. So yeah, if you kind of want to read more, because this technique can be applied even for different quantum computers, just same goes to aggregation or sharpening, right? So yeah, using plurality or majority voting, in the white paper, it demonstrates that it actually works quite nicely. To enable it in Qiskit or Cirq, it's basically those additional parameters you submit to your job, right? Enabling debiasing and sharpening. You can actually have debiasing enabled, but not sharpening. So remember this example I mentioned with the quantum chemistry? You can have debiasing, and it will help with the results. You will see less noise overall, so your profile will be more smooth, right? But please don't enable sharpening there. So just put sharpening into false, right? Or just simply do not even specify it at all. So that's how you can use it in majority languages. I think I mentioned before that examples available on Amazon as well as Microsoft. So if you just look at the GitHub, let's say Amazon bracket examples, right, under the bracket features, error mitigation, if you just look for error mitigation, you will see examples of submitting your job. In this case, it's Aria, actually one of our, it's not the latest. Forte is the one available right now, the latest one. But with Aria, you still have like 25 qubits you can use. And it's available for general public without even reservation of the whole machine. So, which is pretty nice. All right, so all right, where are we at right now? There, yes, this example I was showing on Aria, it's just basically, yeah, it just demonstrates that you can have kind of debiasing off, debiasing on. It will improve the answer, but if you only looking for a sharp answer, then with sharpening, it helps sharpen it quite a bit. All right, so let's see how good. Whoa, I almost on time. Okay, 38 minutes, perfect. So I think I'm ready for questions. Once again, if you want to learn about GPU devices, you can directly go to IonQ. And under the cloud, well, you can register for free to get the access to the simulators, but also you can read more or kind of get more information about the backends by just going to the cloud, ionq.com site, right? And basically all the devices like Forte, how many algorithmic qubits available there, overall qubits, gates supported, right? Information about the fidelities, all is available on the portal itself, but also you can find this information on the website if you don't want to go through the registration. And basically, here we have all the information about currently available devices to all the public, right? I mentioned Forte, Aria 1, they usually something, and the Harmony, one of the previous generations. Also, if you want to play with the simulator, there's Ideal Simulator, which is available completely for free, but also we reproduced the behavior of Aria and Harmony, and you can simulate, you can have basically noisy simulator. So if you can see if your algorithm will be performing nicely, even with real quantum noise, although you're going to be simulating it, right? You can try to use this noisy simulators to see how big your circuit can be or how wide, right? So you can play around with all the noisy simulators as well as QPUs as well, and that's how you basically can get familiar with the IonQ QPUs. All right, so questions. Let me quickly take a look at Twitch and YouTube. to see if we have any questions.
Yeah, thanks, Vadim. I actually have the questions written down here, so I'll ask you them here. Thanks for that. That was really interesting. I really appreciate your time. That was really interesting. Very thorough. Thanks.
Tried my best.
Okay, so we have a question from Broken Symmetries. This was earlier on in your presentation, I believe. Phase, sorry, let me go back to the interview. There we go. Phase is measured with respect to an origin. So when we say control the phase of a pulse, what is the frame of reference for that phase?
It's a pretty loaded question. So basically, the frame of reference during the. Let me actually go to the slide. Maybe it's going to be easier. Here we go. So during the initial stage, when we're doing all the calibration of the devices, that's where the frame of reference actually coming from. So we start experimenting, right? And yes, you're absolutely right. When you just interacting with photonic beam, right, with the ion, any shift or any even vibration in the ion itself might produce the results which you're not expecting ideally, right? So we always kind of doing those calibrations where we simply producing kind of test interactions first, and then measuring the result of those interactions. And if we expect a particular one, we can then calibrate or adjust in this case, specifically kind of phase, right? And that's how we define the point of reference. So we kind of trying to adjust those parameters to get as close to the expected modification or expected interactions with the photons, if it makes sense.
All right. Well, Broken Symmetries, right back in the chat if that answer didn't satisfy you. We had a lot of questions about like the sharpening part. So there was like debiasing and sharpening. If you can go back to that slide, maybe that'd be useful. Yeah, we'll start here with Dentucky Kirby. This sounds like you're just tossing out the wrong answers, but I know it can't be that simple. So why is that wrong?
It is actually. It is the right approach. We simply tossing out the wrong answers. Yes.
Okay.
It is what's actually happening.
Okay.
Yeah. So just because we have 25 or about that amount symmetric variance which contribute to the answer, so probabilistically, the correct answer, if you expect to have only one bump, right, one correct answer, or maybe just a few of them, you will observe them more often than just quantum noise.
Okay.
You can probably do the calculations when this hypothesis is going to be broken, right? It depends kind of on how noisy your system is, but like, yeah, it's can be calculated. But the whole idea is exactly, you're absolutely right. The whole sharpening technique is getting rid of these error contributions due to the quantum noise, and only collect those where we expect to have the correct result, right? And we hope that it's going to be observed, or those results going to be generated by more symmetric variants compared to just those erroneous results.
Okay. Couple more questions on this.
Yep.
So Broken Symmetries has another question. Are these debiasing and sharpening techniques better suited for trapped ion devices, or would they work equally well in other devices and other hardware?
I think it can be applied to other devices as well. So if, let's say, you have superconducting implementation, or maybe even optical ones, right? Having those symmetric variants will help you to get rid of the systematic error. So I would say yes, those techniques. It will be slightly different physical implementation, right? And or maybe there will be some nuances and specifics depending on the qubit implementation. But the general idea can be applied to pretty much like any qubit implementation.
Okay.
Or physical, yeah. Yeah.
Okay, one more question about this sharpening stuff from Ket Punto. Hey, is the QML field suitable for these sharpening techniques? So similar to be like, I don't know, maybe there's like some error in your model and like, or just noise in your model, and you could just, I don't know if it's applicable there. Somewhat unrelated, but also kind of adjacent.
Yes, I think. Well, QML. There are different implementations, right, and different problems in QML. So, unfortunately, the question is too generic. I would say if you kind of expect that there will be only a particular classes,
right?
If it makes sense, right? Then yes, sharpening can be still applied there. So once again, the whole classification, the whole criteria, if you can apply sharpening or not, is based on what answer you expect. If it's going to be just a couple of few answers, right? Then yes, sharpening works perfectly because like it will simply dump or get rid of this quantum noise and only amplify your correct answers or kind of expected answers. But if it's somewhat profile, so if you have a lot of classes, or once again, depending on the problem you're trying to solve, if it's just a conversion function, then probably no. Sharpening will ruin it because it can messes up with statistics aggregation, if it makes sense.
Okay. Right. Okay. One question from Andres Ulid. Hi. How to make error mitigation with IonQ? Can the error mitigation that comes from Qiskit, like zero noise extrapolation, etc., from an estimator, be used with quantum computer for IonQ?
I think it can. I can probably follow up if it's something you're really interested for your research. I would recommend just to quickly go take a look at IonQ website, where just search for error mitigation. And if you will not find the answer, I can probably just follow up with you. Just email me at korpusyanka@ionq.com. And I know exactly the person I need to ask this question who exactly know the answer. So yes, please, if it's something your researchers depend on, follow up with me. I would gladly find you the correct answer.
Maybe a good question for the Discord. So Andres Ulid, maybe if you want to hop on Discord after.
Yeah.
Great.
Perfect. I will be on Discord, by the way.
Right.
Yep.
Exactly. I guess maybe a fun one. I see your QHack shirt back there that you got last week.
Yeah.
You have some nice LED light strips everywhere. What's going on there? I know you've blurred your background, but
so, all right. I'm always telling this story. I think that's one of the reasons why I got a job at IonQ, because while I was going through the interview a year ago, a little bit more, I gradually started building this thing behind me.
Okay.
This padboard, and the main reason was I had very messy table with a couple of computers, tons of wires, and I thought I need to put them somewhere. And I thought, what can I do? And that was the obvious solution. Let's just put the padboard, and then like it started growing, and I'm like, it's ugly. How can I beautify it? You know? Okay, LED strips. Yeah, that works.
Yeah.
And basically just say, let me just put a couple of those around. Like, hey, it looks nice. And people always have the kind of question, so what is this? Like, oh, yeah, that's the thing I built myself. And my kids, I have two kids, 5-year-old and 2-year-old. They like to mess with it. And you can control it actually remotely. So, a lot of fun. It's almost like a hobby project for me.
Yeah. Nice. Cool. Definitely love a good Zoom background that's authentic and not like a fake one. So congrats. Nice. All right. We're ending really just right on time, Vadim. So I really appreciate it. And again, anybody have any questions for Vadim, go to the Discord. That's where it's happening. So go chat with Vadim there. Vadim, thank you so much for being a big part of QHack this year, last week in the in-person stuff and virtually here today. Thank you so much. Enjoy the rest of your day, and we'll chat soon. Take care.
My pleasure, and thank you for amazing audience. You did a great event, and all the people I have a pleasure to talk with, like, mind blowing, amazing. I love the community.
Yeah,
awesome.
Thanks, Vadim. Cheers. Have a great day.